An alternative graphical display for quantitative data is called a stemplot. This stemplot is a shortened version of the more common name, stem and leaf plot. It's called a stem and leaf plot because it's basically what it does is it takes your quantitative numeric data and it splits it into a stem and a leaf. So by definition, the leaf will always be the rightmost digit in your number, whereas the stem will be everything but the rightmost digit. Okay, so that makes sense now to do some type of scenario or example here just to show you what this even means, right? So let's just pick a number. Let's say we have the number 72. So the first order of business for creating a stem plot is to break 72 into pieces, specifically into its stem and leaf. I always communicate to students that the best thing to start with is the leaf, because the leaf is easy to pick out. It is always going to be the rightmost digit. So in this scenario, we know that the leaf is going to be 2, which is the rightmost digit. Therefore, the stem must be everything else. Well, the only everything else in this number is the 7. We will be making the literal stem plot in a second, the actual graph, which will require us to separate these numbers. So all we're doing is doing a little exercise here to make sure you know how to do so. Another example would be the number 115. So we know that a digit means single digit. So that means the leaf of 115 has to be 5. But the stem is going to be everything but 5. We have more this time. It's like we have 2 digits, but that means the stem must be 11. Okay, now that you know how to break apart a number into its stem and leaf, the next thing to do would be to jump right into creating this new graph called a stem plot. What you see here is a generic bunch of data. We're going to be taking this data and making a stem plot out of it. The first type of stem plot we're going to be using is one that is one line per stem. This will make more sense as we complete our graph, because what we'll do after that is make 2 lines per stem. Okay, you always start by drawing a vertical line like this. The goal is, right off the bat, is you want to look at what your stems are going to be. So in the logic of what you just learned up here, basically, you want to look at what would constitute a leaf in this problem. Well, a leaf is the rightmost digit. So that means those are only going to be the digit all the way on the right, which means the stems in this problem will be the double digits on the left. So for example, in our first number, our lowest number, we have 19 as our stem. So these numbers are in order. So therefore, that is going to be the lowest stem that we're going to have to deal with. So that's going to be our first number that we're going to place over here. Now what we want to do is we want to go find our highest stem, our largest stem. So we're going to go to our largest number over here, and it looks like 22. So what we need is we need all the numbers, integers, that fall between 19 and 22 on the left side. So we have 19, 20, 21, and 22. The next step is to incorporate the leaves. So what we're going to do is we're going to list out every leaf to the right side of the vertical line, the right side of this right here. So as we go through the data numerically, so we got 199. So that means we have 19 and 9, as in 199. Now that's the only leaf that has a stem of 19. There's your leaf. So then we go over to 200 and we go, okay, what's the leaf of our first stem that's 20? It's 0. But then you'll see that we have a lot of values here that have a stem of 20, which means we're going to have to list all of those leaves out after our 200. So technically, this is highlighted too, obviously. So here we go. We got 2 for 202, 203, 207, 208 twice. So when you're making a graph, you want to make sure you include every data value because we need all the information. So just because it repeats doesn't mean anything. We need to know all the data. And that'll constitute that. So just 1, 2, 3, 4, 5, 6, 7. And then we have 7 numbers right here. Okay. So we're going to do the same thing with the rest of the numbers. If you look at our 21 stems, they're going to start here. And they're going to go all the way to here, believe it or not. That's a lot of numbers. So we're going to have to make sure we have all those covered. It looks like we're going to have 4 210s to start. We have a 212, a 213, a 214, a 215, a 217, and 2 218s. Finally, we have one stem of 22 that has a leaf of 1. So this thing right here is called a stem plot. What does it do? It shows out its advantage over the histogram is it actually shows the data points. In a histogram, we might know a span of numbers in some of those histograms, but we don't actually know the data itself, whereas in a stem plot, you do. The negative is, do you really want to sit here and write all these numbers out all day? It's better for small data sets that we're dealing with now. So a stem plot is actually interesting because if you look at it sideways, what you can actually get out of it is a little bit of a shape for this distribution. So it almost looks like, if you looked at it sideways to the right, it looks like a little bit of a histogram. So the problem with this specific looking shape is that it looks like just a gigantic tower in the middle. So it would be kind of hard. It looked like it is skewed a little bit to the left, but it would be kind of hard to judge exactly that because there are only technically 4 classes if this was a histogram. So that's where this guy comes in over here. Instead of making one line per stem, we're going to make 2 lines per stem and see if we can take this graph and spread it out a little bit. So we have a better chance of seeing maybe a shape in the end. Okay, so what does that look like? Well, we're going to have a vertical line, but it's going to be a lot longer. Why? For each one of these stems over here, we're going to be doing 2 of those numbers. So 1919, 2020, 2121, 2222. If you want to think about this logically, the idea is that on this one line right here, for a 1 line per stem, any number between 0 and 9 could go there. Any one of those 10 numbers, same thing on this line. Any one of the 10 numbers could go there. So now what we want to do is instead of 10 numbers being on a line, we want half of that to be on a line, the early half to be here and the later half to be there. So if we have the numbers 0 to 9, if we were to split that into halves, that would be 0 to 4 and 5 to 9, which means this right here is going to be all the numbers between 190 and 194, whereas this right here is going to be all the numbers between 195 and 199. In our problem, we don't have any numbers here between 190 and 194, but we do have a 199, which can go right here. We're going to do the same thing for the 20s. So we can look up here if we want, but we can also look down here because that'll give us the data that we need in a little bit of a nicer view. So the goal is for this guy here, we're doing all the numbers between 200 and 204, and that's going to be these 3 numbers. So that means we have 0, 2, and 3 for the first half of the 20 stem numbers. The other half of those numbers are going to be there. or the other half of the span is going to be there in which those numbers fall in. So we're going to get 7, 8, 8, 9 as the number. So again, this here is going to be all the numbers between 20 with a leaf of 0 to 4, and these are going to be all the numbers of 20 as a stem between a leaf of 5 and 9. Okay, we're just doing the same thing for 21. So this time, if we're going to take all the numbers between 0 and 4, it looks like it's going to be all of those. So we're going to have our 4 zeros, 2, 3, and 4. And then for 21, it looks like it's the rest of them, 5, 7, 8, and 8. And then finally, there's a 221, but there's no numbers between with a stem of 22 with leaves between 5 and 9. So hypothetically, we don't need these two numbers, but we're just going to leave them just for the purpose of understanding the material. One small thing I forgot to mention, which is actually pretty important, just remember the alignment of your graph is really important. For example, if you look at all of the numbers that I made, they're always right on top of each other. You have to do that because the only way you're going to get a judgment on the shape of this distribution is if it's lined up perfectly. If you just squeeze a bunch of numbers and they're off kilter, then you're not going to get a good shape out of this. So make sure that you do that. Okay, so remember we were talking about how it can give you a little bit of a judgment on a shape. You don't really have to do this in your problems, but I like to show it so that you have a nice visual of things. So if you turned your head to the right and looked at this sideways, then you would end up with basically what looks like a slightly skewed left histogram, which means when you were to describe this shape, you would say skewed left. Last thing, whenever you have a stem plot, there's usually what's called a legend at the bottom. The legend basically tells you what each value above it represents, and it usually takes the first number. So for example, we're going to take our first data point, which is 199. So what would the legend say? It would say something like 19 vertical line 9 represents 199. So that the reader will look at it and go, okay, so that's what 199 is. Now, why do you have to do that? Because what if instead of that being 199, it was 19.9? We have no way of knowing what it is and what it isn't. The rightmost digit here, our leaf, would be 9, and our stem would be 19, which is the same as this. So in that case, we would write 19 like this. 19 bar 9 is 19.9. So the legend actually is a little bit more important than you think it would be, just because it's going to tell us what the actual number is.